Hello everybody, welcome back to my channel. This is Dave. So I signed into YouTube today and I saw that I have over 100 subscribers. So first I want to say thank you to everybody who subscribed to my videos, and I hope that you'll keep watching and keep supporting these videos in the future. Since I didn't plan what I was going to say today, I didn't know exactly what I would talk about. However, I remembered this interesting property. If I take 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, it comes out to be 100, which is 10 squared. Now 10 is equal to 1 plus 2 plus 3 plus 4. So it looks like if I take the sum of cubes up to n cubed, it's the same as adding up all the numbers 1 through n and taking the squared. Or is it? That's what we're going to be taking a look at in this video today. So a long time ago, there was a mathematician who discovered the following property. If I take 1, it's equal to 1 cubed. If I take the next two odd numbers and add them, I get 3 plus 5, which is equal to 8, which is equal to 2 cubed. Next, if I take the next three odd numbers, I get 27, which is equal to 3 cubed. And if I take the next four odd numbers, I get 64, which is equal to 4 cubed. So if I add everything on the left-hand side, I get the odd numbers 1 through 19, which comes out to be 100. And on the right-hand side, I get the sum of the cubes 1 through 4, which also turns out to be 100. Now the question is, does this property apply universally? Or is it just some kind of fluke? Or does it maybe apply at the lower numbers? Or does it break down at some very large numbers? To do this, we are going to use a technique called mathematical induction. Now, mathematical induction is a way of proving something, usually for the properties of natural numbers. So we let P be some property of the natural numbers that we want to prove. Then we're going to look for two things. We're going to say if P is true for n equals 1, and if P of n is true, then P of n plus 1 is true. If all of these are true, it means that P of n is true for all positive integers. Now this is just a very fancy way of saying that if P of 1 is true and P of n is true, it means P of 2 is true and P of 3 is true, and so on unto infinity. So how can we use mathematical induction to see if this is true? Well, the first thing we want to do is to express the left-hand side in terms of n. This can be done by writing each line in the form S sub n is equal to the quantity n squared minus n plus 1 plus n squared minus n plus 3, going all the way up to the quantity n squared minus n plus 2n minus 1. Of course, we can simplify this a little bit so that S sub n is equal to n squared minus n plus 1, skipping a number each time and going all the way up to n squared plus n minus 1. For example, if n was 5, then we would have the sum 25 minus 5 plus 1, 25 minus 5 plus 3, and going all the way up to 25 plus 5 minus 1. This would, of course, give us 21 plus 23 plus 25 plus 27 plus 29. Next, we are going to assume that each line adds up to n cubed, and that n cubed is equal to the quantity n squared minus n plus 1 plus n squared minus n plus 3, etc., going all the way up to n squared plus n minus 1. In other words, all of those odd numbers which happen to be on a given row. We want to show that This also works if you replace n with n plus 1. In that case, as we see here, the sum of that particular line would be n plus 1 quantity cubed. In order to do this, we are going to consider some arbitrary non-final term in the sum as sub n plus 1, which can be written in the form n plus 1 quantity squared minus n plus 1 plus b. Expanding the term n plus 1 squared, we get n squared plus 2n plus 1 minus n minus 1 plus b. Combining like terms, we will eventually arrive at n squared plus n plus b. Now we compare this to its corresponding term in the sum as sub n, which happens to be n squared minus n plus b. This means that each term in s sub n plus 1 is 2n larger than each term in s sub n. We can use this fact to write s sub n plus 1 in terms of s sub n. Now, as we just said, each term in the sum s sub n plus 1 is 2n larger than each term in s sub n, which means that we can write the following. S sub n plus 1 is equal to s sub n plus 2n times n plus the final term of s sub n plus 1, which is shown in blue and is equal to n plus 1 quantity squared plus n plus 1 minus 1. We can simplify this a little bit and we get s sub n plus 1 is equal to s sub n plus 2n squared plus n squared plus 2n plus 1 plus n plus 1 minus 1. And then this also simplifies to s sub n plus 1 is equal to s sub n plus 3n squared plus 3n plus 1. However, since we said that s sub n is equal to n cubed, this means that s sub n is equal to n cubed plus 3n squared plus 3n plus 1, which is exactly a perfect cube polynomial, or s sub n plus 1 is equal to n plus 1 cubed. Going back to our original problem statement, we can see that each line contains exactly n odd numbers. Those n odd numbers are the next odd numbers from the line above it. Therefore, if we sum up the left-hand side, we would get the first 1 plus 2 plus 3 going all the way up to n odd numbers. At the same time, it's a well-known property that the first k odd numbers is equal to k squared. Therefore, the total of the left-hand side would simply be the quantity squared. In other words, the left-hand side is equal to the sum of 1 plus 2 plus 3 going all the way up to n, taking that sum and squaring it. Then we can add up the right-hand side, equate the two, and we find the sum of the first n cubes is equal to adding up the numbers 1 through n and then squaring them. Alright, so this was my special 100th subscriber video. If you like this video, please give me a thumbs up and like, and please continue to support the channel. Thank you very much, and I'll speak with you next time.